So last time we computed an indeterminate trigonometric limit problem, which we said was needed to, to compute the derivatives of the sine and the cosine functions. So let's see if today we can go ahead and in fact, compute those derivatives. So we'll begin with the sine function. Okay, so if y equals the sine of theta, then dy d theta, or the derivative with respect to theta of sine theta, is by definition the limit as the change in theta approaches zero. The sine evaluated at the point theta plus delta theta minus its value, the sine's value at theta, all divided by the change in theta. Okay, so that's our limit definition for the derivative of the sine function. So, but in order to evaluate here, we're going to have to do some work. In particular, we're going to expand the sign of this sum using our formula from trigonometry that said the sine of a sum will always be equal to the sine of the first angle multiplied by the cosine of the second. Added to that, the cosine of the first angle times the sine of the second. Okay, so this is simply an expansion for the value of the sine at theta plus delta theta. Okay, and we still have to subtract the sine of theta and then divide by delta theta. Okay, so that's just an expanded form for the previous limit quotient. So at this stage, what we'll do is we'll do a little factorization in the numerator. Okay, notice that this first product involves the factor sine theta, and the last term also is sine theta. So we could factor out the sine of theta from those two terms, do a little regrouping, and rewrite the numerator as, well, let's write, in fact, this middle term first, which is the cos theta times the sine of delta theta. Okay, and then we'll have plus. Okay, then we're going to factor out the sine of theta from the remaining terms. So I'll have sine theta times the product cos delta theta minus 1. All right, and that's all divided, of course, by the denominator delta theta. But if we like, we could kind of split this up into two parts. Okay, into the sum of two fractions. Cos theta sine delta theta divided by delta theta, and then plus this remainder divided by delta theta. Okay, and we recall that the limit of a sum of two functions is the sum of the limits, provided that both of the limits exist. And so we're going to split this now into two separate limit problems. What we notice is this first ratio has a factor cos theta. Of course, cos theta is independent of delta theta. And so that factor could be brought in front, could be pulled in front of the limit operator. So we could rewrite the problem as the cos theta times the limit as the change in theta goes to 0, sine delta theta divided by delta theta. Okay, then plus the second limit, which involves factor sine theta. Again, sine theta is independent of delta theta, so we could bring that factor in front of the limit operation. So we have sine theta times a lim as delta theta goes to 0, cos delta theta minus 1, all divided by delta theta. Okay, and so So we've done a little a little expansion of our limit problem, and what we notice is this first limit, sine delta theta over delta theta, as delta theta approaches 0. Remember, this is the indeterminate 0 over 0 type limit that we had evaluated in our previous video, and we showed that that limit was exactly equal to 1. Now, we're left with another indeterminate limit problem, namely this one, because the cosine of 0 is 1, so this limit is also indeterminate of the form 0 over 0. To solve this problem, we're going to multiply by the conjugate of the numerator, okay, in numerator and denominator. So in other words, we'll multiply this limit by a factor of 1 in the form of the cosine of delta theta plus 1 divided by the cos delta theta plus 1. Okay, so of course multiplying by 1 will not change the value of the limit. Okay, so with that in mind, we see that our formula thus far for the derivative of sine theta looks like the cosine of theta times 1, or just the cosine theta, plus the sine of theta times the limit as the change in theta approaches 0. Okay, now when we expand the product in the numerator, we'll get the cosine squared of delta theta. Of course, the middle terms will drop out, being cos delta theta minus cos delta theta. Then, of course, minus 1 times 1 is minus 1. And then this is now divided by the product, delta theta times the cosine delta theta plus 1. Okay? And so, so what could we say here? Well, if you remember our basic trigonometric identity, we call it the Pythagorean identity, that the cosine squared of an angle plus the sine squared of an angle is always 1. And consequently, 1 minus the cosine squared of an angle would be the sine squared of the angle. And so this quantity, cos squared delta theta minus 1, would therefore have to be equal to minus the sine squared of delta theta. Okay. And so what we're going to do is we're going to use this substitution in our limit, and therefore we could rewrite the limit this way. And in fact, this factor of minus 1, I think I'm going to bring the factor of minus 1 in front of the limit operator. So we'll get minus the sine of theta times the limit as the change in theta approaches 0. And so this sine squared of delta theta, I think I'm going to split that up into two parts and write it as the sine of delta theta multiplied by the sine of delta theta. Okay, instead of writing it as sine squared delta theta. Okay, and now my denominator is still this product, okay? And so I'm also going to kind of split that up and say, well, I could therefore write this limit as sine delta theta divided by this factor of delta theta, and then the other sine delta theta in the numerator will be divided by the cos of the delta theta plus 1. Okay, so all I did was, rewrote the sine squared as sine times sine, and then split up the product in the denominator. Okay, and the reason for doing that, you see, is because now I could say, well, now I have a limit of a product here to evaluate, which I know is the product of the limits, again, provided that both limit exists. And both of these limits are, in fact, easy to evaluate. So finally, we have that our derivative formula looks like the cosine theta minus the sine of theta times the limit as a change in theta approaches 0 of sine delta theta divided by delta theta multiplied by the limit as delta theta approaches 0 of the sine of delta theta divided by cos delta theta plus 1. Okay, so I simply said, this limit of the product will be the same as the product of the limits. But remember, this first limit, the sine of theta, the sine of delta theta over delta theta, as delta theta tends to 0, that indeterminate limit must equal to 1. And what do we have as our second limit in this product? Well, we know, of course, as delta theta goes to 0, the sine of delta theta tends to the sine of 0, which is 0, right? In the denominator, we get the cosine of 0, which is 1, plus 1. Okay, so 0 divided by 2 is equal to 0. This limit is not indeterminate. It equals to 0. And so therefore we see that the derivative of the sine of theta will be equal to the cosine of theta minus the sine of theta times 1 times 0. Well, the sine of theta times 0 is 0, and thus we can conclude that indeed the derivative of y with respect to theta, or in other words, the derivative with respect to theta of sine theta, must be equal to the cosine of theta. Okay, so that would be our formula for the derivative of the sine function. Indeed, it equals to the cosine of theta. And so you say, well, that's very good. Well, what about the derivative of the cosine function? Could we compute that derivative fairly easily? And in fact, that won't be too much of a problem at this point. So let's again write out by definition the derivative of the cosine of theta. So in this case, dy d theta is given by the derivative with respect to theta of the cosine theta, which will equal to the limit as the change in theta tends to 0. We're going to take the cosine at theta plus delta theta minus the value of the cosine at theta divided by the change in theta. Okay, so again, that's just our limit definition for the value of the derivative of the cosine function. So again, we'll have to expand the cosine, this time the cosine of the sum, in the numerator. Okay, so if you recall the formula for the cosine of a sum, we take the cosine of the first angle, which is theta, multiply it by the cosine of the second angle, delta theta, okay, and then we subtract the product of the sines of our two angles, minus the sine of theta times the sine of delta theta, okay. So this is the expansion for the cosine of theta plus delta theta. And from this, we still have to subtract the cosine theta, right? And then divide the whole thing by the change in theta. Okay, so that's our formula for the derivative of the cosine theta. Now to evaluate it, we're going to notice that in the numerator, the first term has a factor cos theta, as does the final term. So again, we're going to regroup the terms in the numerator a little bit. So let's rewrite the limit as, well, let's write this middle term first in the numerator. So we'll have, minus the sine of theta times the sine of delta theta. Okay, and then we'll put the plus, okay, and then we have the cosine theta that we're factoring out of the other two terms. So the cos theta times the quantity cos delta theta minus 1. Okay? And now this whole thing would be divided by delta theta, but in fact, we're going to think of this as two separate fractions. So we'll take this first product divided by delta theta plus the second part here divided by delta theta. So we need to find the limit of this sum. Okay, so again, the limit of a sum would be the sum of the limits, again, provided that both limits exist. And the first limit involves this factor minus the sine of theta, which is independent of delta theta. So we bring that factor in front of the limit operation. It will then be multiplied by the limit of sine delta theta over delta theta. Okay, and then similarly, the second limit, the factor cos theta is independent of delta theta. So let's bring the cos theta up front. We'll get the cos theta times the limit as delta theta goes to 0, the cosine of delta theta minus 1 divided by delta theta. Okay, so we simply have to consider now these two limits on the right side. So what we know is that, again, this indeterminate limit, right, we solved sine delta theta over delta theta converges to 1 as delta theta goes to 0. And if you look at the other limit involved, the limit of cos delta theta minus 1 over delta theta, which is also indeterminate 0 over 0. But if you notice, that was exactly the same limit that we had, problem that we had involving the derivative of the sine function, right? Had the same limit here that we found ultimately to have value 0. So this limit, we know by our previous analysis, must be equal to 0. And so after all this, we see that, in fact, the derivative of y with respect to theta, or in other words, the derivative with respect to theta of the cos theta is going to be what? Minus the sine of theta times 1 plus the cos theta times 0, which just simplifies to minus the sine of theta. And so we found the derivative of the sine function to be positive the cosine, the derivative of the cosine of theta to be negative the sine of theta. Okay, so we will be using derivatives of the sine and the cosine functions quite frequently in problem solving throughout the remainder of the semester. I hope you enjoyed this lecture. Goodbye.